done a few videos on my channel recently about how to make piecewise functions continuous. Well, what if you have a function or a piecewise function that has a whole discontinuity? In other words, you have a function basically with just one little point, one hole taken out of it. How do you make that piecewise function continuous? Well, today I'm going to be showing you exactly how to do that. And I'm going to show you how to do that with an easy example. Well, the example's not easy, but I'll show you that the process is really pretty easy. So when you're done with this video, you should be able to do these whole discontinuity piecewise function problems all on your own, nice and easily. Let's go ahead and just jump right on into it. So here's the problem we're going to be going over today. We're going to find the value of c that makes this piecewise function continuous everywhere. Where we have this piecewise function where we're using this function x squared minus 4 all over x minus 2 whenever x is not 2. And then when x is 2, the value of our function is just going to be c, or the output of our function will just be whatever c is. So when you're doing these types of problems where you're trying to find some constant or make sure that some piecewise function is continuous everywhere, basically what that's saying is you want to make sure that your function is continuous for all x values. Well, when you have a piecewise function like this, essentially what that is just different chunks of different functions kind of put together into one big function. So we know basically that this piecewise function specifically is going to be the makeup of these two functions, and whichever x value you're looking at tells you which function you actually want to use to get the output at that point. Well, in order to make sure that the whole piecewise function combined is continuous everywhere, there's kind of a couple different things you want to think about separately. First of all, we need to make sure that each of these pieces of our piecewise function is continuous just within their restricted domain. So basically, we know that we only want to use this function to define our function f of x when x is not 2. So what that means is we want to make sure that this function is continuous whenever x is not 2. If it's not continuous when x is 2, that's okay, because that's not a part of this restricted domain. When x is 2, we want to make sure that this function is continuous because x equals 2 is this function's domain. So how do you figure out if this piece of a piecewise function is continuous in its domain? Well, typically there's going to be three things that you want to look out for, three things that are going to cause discontinuities. And that is going to be dividing by 0, taking the square root of a negative number, or taking the log or natural log of 0 or a negative number. So the reason why these are the three common things to look out for is each of these three things essentially breaks the rules of math. You can't take the square root or any even root of a negative number. You can't take the log of 0, you can't take the log of a negative number, and you can't divide by 0. In this case, obviously we don't have any square roots, we don't have any logarithms. So the one thing that we really want to be careful of is not to divide by 0. Well, if we look at this function, obviously we have a fraction. So if this denominator here equals 0, if x minus 2 equals 0, what that's going to do is it's going to cause us to divide by 0. So we need to make sure that's not happening. Well, basically to figure that out is if you make x minus 2 equals 0 and solve for x, that tells us the x value that would cause us to divide by 0. Well, you can see the only x value that causes us to divide by 0 in this case and break the rules of math would be x equals 2. However, notice x equals 2 is not in the domain of this function. Only all x's besides 2 are in the domain. Pretty convenient in this case that the one point we don't actually want to look at is the point that's not in the domain. But that's what gives this piecewise function a chance at being continuous everywhere. So we know that the only x value that causes this function to not be continuous is the one that's actually not included in its domain. So that's good. That's a good sign because that means this chunk of our piecewise function within its domain is continuous throughout its entire domain. Now we also want to consider this other piece of our piecewise function. Well, this piece of our piecewise function is just a constant, right? Like y equals some constant. We know that a constant function is continuous everywhere. So even if this wasn't restricted to just x equals 2, this function would be continuous for any x value. Therefore, it's definitely continuous for x equals 2. So we know that both pieces of our piecewise function are continuous within their domain. However, now what we need to figure out is making sure that our function is continuous when we switch from one domain to the other. So in other words, when we get, if you kind of imagine Imagine you have some function, and this is not necessarily what this piecewise function is going to look like, but imagine you have some function that you're kind of coming along from negative infinity from the left, and then you get to this point where you're now switching to some other function which is defined in another place. That point where you switch from one function to the other is where we need to make sure that this is continuous now, because we know that it's continuous everywhere else, right? So this is, an example of what this could look like. Again, that may not necessarily be what this piecewise function looks like. But the point there is that we need to now make sure that this piecewise function, when we switch from one function to our other function, which occurs at x equals 2, we need to make sure that they line up with each other at that point. So basically the idea there is we need to make sure that these two functions have the same output when x equals 2 at that very specific input. To do that, all you really have to do is set those two functions equal to each other. So we're just going to set x squared minus 4 all over x minus 2 equal to c. And specifically, we need to make sure that those two things are equal when x equals 2. They need to line up at the point where we switch from one to the other. Before we do that though, I do want to point out one interesting thing about this specific function, because notice what we have here on the top is a difference of squares. We have a squared term minus another squared term. So what that means is we can actually factor this numerator out to x plus 2 times x minus 2. And then of course that's all over x minus 2. So what you may notice about this is both our numerator and denominator have an x minus 2 term in them now. So what we can actually do is cancel these out. So what that means is this function that we started with for this chunk of our piecewise function, the x squared minus 4 all over x minus 2, is actually exactly the same as the function y equals x plus 2, except at x equals 2, where we break the rules of math by dividing by 0. So basically what that looks like on a graph is the function that we started with looks exactly like this linear function x plus 2, which looks something like this, except one key difference, there's going to be a hole where x equals 2. So right here, there's actually a hole in our line. Other than that though, it's exactly the same as that linear function. So basically the idea here of this piecewise function being continuous everywhere, obviously this part of our piecewise function is discontinuous at x equals 2. But we know that it's a whole discontinuity. In other words, it's a discontinuity that's formed by creating some continuous function and then just taking one little point out of it and making a hole there. So what we're trying to do is pick our c so that it fills that hole, basically. And where that will occur is when x plus 2 equals c and when x equals 2. So if we take x equals 2 and plug it in for x here, that will give us that c equals 4 will create a constant function at 4, which means when x equals 2, y equals 4, well, guess what? That happens to be exactly this point right here. So making c equaling 4 fills in that hole and makes this piecewise function continuous everywhere. Hopefully you found this video helpful. If you did, please be sure to hit that like button down below and hit that subscribe button and the bell icon while you're down there too. It really does help to support my channel so I can keep making more videos like this. And if you want to learn more about piecewise functions and how to make sure they're continuous everywhere, go ahead and click on one of those videos over there. Thanks and see you next time.